finished talking about dimensions of the frame. Now, last time we've seen the X and Y axis of the frame and how to dimension everything. Now, for the Z axis, it should be the same, so I won't go through all the passages, just to show you, mainly using the same technique that we used the last time, how to do the same with the Z. Now, cameraman, please come closer. Okay, so here you can see that the Z-axis on my printer is held by the 4 screws that are moved by the motors downside on the frame. Now, this is the third iteration of my Z movement of this printer. First, when I started, I tried to use, as you know, the less expensive way, which was just using one motor per side, using only 2 sides, so 2 motors, and some smooth rails to keep it in place. So there were 2 bars, like this one, 2 smooth steel rods. This one is 18 millimeters diameter, with some linear bearings, like this one, which, as you can hear, is quite cheap, not so much in quality, but you know, less expensive was the way. So this was the less expensive. Anyway, there were 4 of those rods, exactly where you see now the 4 screws. And there weren't those screws. There were some smaller, cheaper screws, which were 12 millimeters on diameter. Those are 20. Now, as you may imagine, there are no more bars, and there are the bigger ones now, because well, when you try to spend too little, also the quality that you get in the end is quite little. And in this case, the problem I didn't know about, because I always seen those 8 millimeters bars on smaller printers, they do not bend when they are like this tall. But when they are more than 1 meter, well, they tend to flex quite a little. And that's bad, because the first time I tried with those rods, I repeat, 8 millimeters rods, I had bendings all the way. Yes, it worked. The 2 motors made possible for the bed to go up and down, but not so easily. It was shaking all the time. The rods were bending, making the bed not flat at all. It was going like this way while going up and down. Of course, every print I tried the first time went right inside the bin, because well, there's a most directions. No need to show the cameraman, please. So thank you, cameraman. So and well, what I was saying, yeah. So first thing I tried was replacing the highly inefficient rods with 4 screws, and since also the 12 millimeter screws weren't that solid, I decided to go on a simpler movement schematic, let's say it that way. So I chose to put 4 very large screws and use them for movement. Anyway, it's the easiest way. Just use 4 screws, 4 engines, if you can sync them quite good. Otherwise, you better use a closed loop belt with 1 giant motor. Because that's fun. But as you will soon understand when we will talk about motors, when you choose the electronics, you are bound to the drivers you choose. Now, we're trying to spend as little as we can. So we won't go for expensive drivers. We'll try to go for the DRV 8255, which are strong, powerful, yet they don't go quite good with something that some motors that you usually drive with 3 amps, 4 amps. No, they say you should stay around 2.2, 2.8 maximum amps for engine. So, well, that's what they say. I'm actually using 2 engine per driver on the Z-axis. As you can see, there is a parallel connection over there. So I'm driving 2 of these big NEMA 17 motors with a high torque. You can see they are also quite tall. And so this is a cheap solution which let me use 1 motor per screw, and it works. Actually, there was a problem. At first, as you can see, this was the old design, where you can see also the smooth road. Of course, there was a specular one on this side, but I want to show you the more detail I can, so I zoomed only on one rod with the engine. So this was how it worked. There was the screw, the coupling, and the engine, the motor. And this motor had a problem with this configuration. Now, even if I've been using the same thing till last month when I upgraded the, the schematic, the problem I didn't notice at first was the weight. Because when I used the old 12 millimeters screws, they had a weight which was quite uh, light, let's say. They didn't weight much, even they were made of steel like these are, but maybe the diameter, which was almost half of the diameter of current screws, um, it wasn't so much for those engines. But when I switched to those 20 millimeter screws, well, they are quite heavy. And I didn't notice that those motors could not be responsible also for the weight that was pushing on them. So there was some resistance on the movement. Actually, it was not, let's say, um, you couldn't notice that while you were making tests. No, it showed up later when I applied the bed, which is made of an aluminum foil and a small. There are just some beams which the panel is screwed on, and it was not so heavy, but actually it made the difference when I started moving it. I heard a lot of noise from the motors, and when I started holding the screw by hand without a bed, just to see if could be capable of moving it, I would notice that with just my hand, I not even holding it much strength, I could stop it, and that was bad. Not because maybe there was not much power, since remember there are 2 engines on 1 driver, which is not good, but it works. Mainly it was because of the weight of the screw. So I took the opportunity, sorry, to also enhance the quality of the prints, because I had an issue while driving it directly. For example, well, this thing, as you can see from the lines, the Z part of the machine wasn't this precise. You can see there are thicker layers, some lighter layers, thinner layers, sorry. Some are thicker, some are thinner, and this crap. That. So, I needed more precision. So, 2 things I need. There were more precision, and I needed to relieve the motor of the weight of all the structure. So, what I did was apply a reduction, and this helped me As you can see, camera, please come closer. Oh my. This way, having the motor not anymore under the weight of the screw, the only thing it needs to do is rotate the screw, which is actually what we want from the motor and nothing else. So, since I had to decouple the screw for the motor, I also added some gears. Now, I hadn't much space to work. I mean, the bigger the gear I use under the screw, the bigger reduction I get. So I have a more powerful and more precise movement. Let's use a drawing that we have from the CAD to help us better understand. So this is exactly what we have down there. Now we have the motor moving a 20 teeth gear, and the screw is driven by a 50 teeth gear, sorry. So what we have now is a 2.5 reduction, which means that I have more than double precision and more than double power from the motor to the actual screw. Now, this helped quite a lot because, as you can see, we moved from this crappy thing of uneven layers to, for example, this. Now, there is still some more work to be done, as you can see, as the layers are not even close to perfection, but they're quite better than for example, on that print. And that's only because I have added some reduction. Now, there are many more ways to improve precision, but maybe we'll talk about it on the next video. So, since on this video the goal is to show you how to dimension the Z-axis, which is the lifting part of this printer, well, let me tell you something first. Many printers differ on this kind of printer, I mean the Core XY machines. They differ on one main, not peculiarity, design choice, okay? Some printers move the bed up and down, like this one does, like the Replicator one from MakerBot does, like the Ultimaker does. Many other machines tend to move the extruder, its rail, and all the X and Y part of the machine. Let's say the carriage, the wall carriage, both on the Y and the X are mounted on a subframe, which that subframe is moved up and down while the bed stays on the floor. And it's quite easier when you have, for example, a glass bed, maybe with a thick sheet of glass. And I'm not. I have a very thin aluminium foil as a bed, which is not perfect, mainly not because the PLA won't stick to it, and I had to use glue and other things to make it stick to the bed, but mainly because it's totally uneven. Me and the cameraman tried to bolt the, no, well, not bolt, to screw it to the chassis. I mean, there's this little chassis down there, but we only make it worse. There are like many hills over it, but for now it's okay. I mean, we can make a workaround on our prints to avoid that. On a later upgrade, we will change it to a better bed. Now, but it's not the case now. So, I was telling you about the z-axis and the dimension that you have to keep in mind. Now, the only thing you always need to keep in mind is how much you want it to go. For example, you want your bed to go up and down by 1 meter. Very well. Then, all you have to keep in mind is on your chassis the height of the tip of the hot end, because you can see there is some size which is about this size, which is the length from the tip to the, in this case, the upmost part of this rail, because as you can see it's on the same height of the chassis, keeping all together. So um, this will be the first size you have to keep in mind. You can try with inventor, always keep yourself safe. If you think this will be 5 centimeters, make it 10. And after that, you have to calculate how high will be the, I don't know the English name of this thing. Anyway, the part that goes up and down on the screw when it rotates. Anyway, keep in mind all this block, which goes from the upmost part of the bed to the lowermost part of this part. Last but not least, the reduction part, which I had to calculate later, and it was not included in the first design, but I suggest you go and calculate the wall part. Now, the motor can be housed downside. You can have it down the plate. I could do that, but I would only use 2 of the screw holding this motor together, because the other 2 would go against the 50 teeth gear, which is something I don't want. So I prefer to move it on the other side, up here. Which of course is a problem, because when the bed goes down it could strike the motor, but it's not an issue, because since luckily I um, made the movement, the sure movement, about 1 meter and 10 centimeters. Now those are about 10 centimeters, so I'm not losing my full meter, which I wanted in the first place. Just give me a second, please. Okay, so on your design, keep in mind maybe if you want to use the same setup as I did, um, the length you have to keep in mind would be from the top of the motor to the bottom here, which is the utmost part of this aluminum chassis. Let's sum it up. So we have to keep in mind the length of, which goes from the tip of the hot end to the utmost part of the rail which moves the carriage. We have to sum the this thing which I don't remember the name, sorry, which goes from the down part of it to the upmost part of the bed. Last, we have to add the length which goes from the top of this motor to the bottom of the whole thing, which should be this upmost part of this aluminium chassis. So, sum it up with your meter and 10 centimeters just to be safe, and then you have your Z axis. And of course, I was almost forgetting, since we are talking about the chassis, you have also to keep in mind the size of the beam, of course, not only the, the screw, and this will be your screw. Now, how you lock it, I mean the screw to the chassis, it's up to you. You have many ways to do that. I have personally used normal skateboard bearings like these, which are very cheap. You can find them at any sports store. We usually pay like 12 euros for 10 of them. very cheap and do the job quite well. So since you have to make it from a, well, at least you have a lathe, you will have to call a machine shop, someone who can do that for you, because those are machine parts and there is no way you can work around that. You can avoid using linear rails as I did by using those with custom printed trolleys, carriages. Anyway, but you can go without a machined screw. So while you do that, you could also have your tips made like 8 millimeters in diameter, so you can use skateboard bearings. And in the downmost part, you can go always 8 millimeters, or you can make it 5 if you prefer, if you find your gears, which I repeat is a must. You have to reduce by gears your movement, otherwise torque won't be enough. I mean, with such small motors and such a big chassis. So let's sum it up again. I mean, not the size, I mean the wall Z part. And on the next video we will talk about moving X and Y. This one we've seen how to dimension and move on the Z axis. And well, the choice is up to you. If you have a very heavy bed, you could move up and down the carriages by making a frame like this a little smaller and then move it up and down. Or you can do as I did, keep the bed as light as possible and move it up and down, because keep in mind also that in the first case you should have a thing going up, so the strength required on the required to move everything would be heavier than maybe just letting this bed go down, because when it goes up for the homing, it will be without load. There won't be nothing printed on. When the print would be finished, you could have 3 kilos of PLA like those 3 coils printed, and it would be 3 more kilos going down now. But they will be going down, not up, so who cares? We don't. So, should be everything. If I have been unclear on something, if I have been forgetting something, or maybe there's something you would ask, please do it in the comments below. Till next time, bye bye, see you soon.